Hi everybody, in this last video, let's cover some surface normal vectors for electromagnetics problems. So you probably, in your Calculus 3 class, you probably found a way to find a normal vector for some arbitrary surface. If you look up surface normals, you might find something like this Wolfram article, which tells you how to do this. It's a little bit more complicated than what we did for a function that was just a line, but it follows a lot of the similar paths. Basically, what you do is you find, instead of finding a tangent line, you find a tangent surface. You do that using partial derivatives and the gradient of your scalar field. Then you get tangent and binormal vectors, and that are on the tangent surface. Take the cross product, and the cross product of those gives you a normal vector, and then you could normalize that vector to get a unit normal vector. And so basically, if you had, imagine you had like an arbitrary surface underneath this green plane, right? You could find the normal vector to that arbitrary surface by finding a B and a T. So find a B, T, and then get a normal vector. So it's a little bit more complicated, but in electromagnetics and engineering, right, we often want to try to solve problems that are more simple. And so that usually means we aren't dealing with some kind of arbitrarily shaped surface, something that is kind of lumpy or uneven or weird. And instead, we're dealing with a lot of shapes that correspond very well to our orthonormal coordinate systems that we use. And we end up using this quite a bit for various problems, especially for problems like where we have surface integrals, which surface integrals are often written like this on the left-hand side. But on the right-hand side here, right, this is an equivalent, and we can see that the field is dotted with a normal vector. And so it's important for us to be able to find or understand by looking at a various shape and a given surface what the normal vector is, because that might allow us to more easily select a differential surface area that we need in a problem. And so in engineering and a lot of the problems that we do in this class, right, we deal with these orthogonal coordinate systems, so Cartesian, cylindrical, spherical, and the normal vectors are usually going to be, so the normal vectors for shapes in these coordinate systems are usually going to be one of the base vectors. So for Cartesian, right, the base vectors are x hat, y hat, and z hat, whereas for spherical, it's phi hat, theta hat, r hat. For cylindrical, r hat, theta hat, z hat. And for shapes in these coordinate systems, it's a lot easier to find the normal unit vector. So let's just take an example, like if we were trying to find a normal vector to this surface. So what is the normal vector here? Well, we can see on this surface we're moving in the x and z direction, like as we move around on this surface, and the normal is y hat. We could also do this for the bottom surface. So if we were just to consider this bottom one, what is n hat? Well, on the bottom surface there, if you are to move around on this surface, you're changing in the x and y directions, and the normal vector is z hat. So by using these like a cube or a rectangle in the Cartesian coordinate system, it's often pretty easy to figure out what the normal vector is if you have an object, a convenient object in that coordinate system. And you can do this for the cylindrical. So for this surface, we can see that the normal is the z hat. For this surface, on this one, right, the normal vector for that face, right, that one's going to be phi hat. And this is all, again, this is just due to looking at the base vectors. So looking at the base vectors and seeing which one of the base vectors is normal to that surface. Or in this case, you can see on this surface, as you move around on this surface, you're changing in the r and the z direction, which means that the normal would be phi. It gets more complicated, and usually the types of problems we don't do are ones like this, where the normal here is going to require a lot more work to solve for. you would have to apply some of these methods used from your Calculus 3 textbook. Lastly, for the spherical coordinate system, right off the surface, the normal, that's going to be r hat. And then depending on the orientation, so which way you slice it, the normal here, right, is either going to be theta or phi, depending on which way you have your sphere oriented in your coordinate system. So I hope this gives you a little bit more insight into surface normal vectors, why we might use them, and also kind of relating them a little bit to these surface integrals, which will appear quite a few times in our electromagnetics class. Thank you, and see you in the next video series.